Hello, in this video I'm going to give you a very brief introduction to the finite element method. The finite element method is a very general technique for finding numerical solutions to differential equations. There are many different types of finite element method, and finite element methods are becoming increasingly popular for modelling the atmosphere and ocean. This is an example of a finite element grid, of a triangular grid with local refinement around the British Isles. This would be for ocean modelling. Finite elements are also useful for cubed sphere grids like this one, which is currently being considered by the UK Met Office. So I'm going to describe how you solve the 1D Poisson equation using finite elements. So this is the unknown variable. The dependent variable is u. We want to find u such that the second derivative of u is equal to a known function f in a domain for x between 0 and 1 with boundary conditions 0 at each end. And we will assume that we're given a set of basis functions called phi I. We've got n of those, and we want to find solutions of the form a sum of these basis functions. So I've got these constants big U, so we've got a sum of these basis functions will give us our solution, our approximate solution. So the task is to find what these values big U are. There are many different possibilities for basis functions, and some basis functions lead to very well-known numerical methods. So for example, I'd like you to have a think if you can think what these numerical methods might be, or you might like to Google them before the lecture, find out what they are. If you have global Fourier modes, this is a numerical method that you know. If you have piecewise constants defined in each region separately, this is another numerical method that you've heard of. Piecewise polynomials defined as non-zero on each element. Well, this is the standard finite element method, the classical finite element method. If you have higher order polynomial basis functions, for example 4 or 8, there's a particular name for that type of finite element method, and there's another name for the numerical method for if you have discontinuities between elements. So we're going to describe how to solve the Poisson equation using piecewise linear elements. So piecewise linear elements look like this. If you've got your grid going from 0 to 1, each a distance delta x apart, a piecewise linear element will look like this. So it's 1 at your grid point and goes down to 0 at either side. So I'd like you to write an equation for phi I given this drawing. Now we had the boundary condition we had with its 0 at each end, which these basis functions satisfy automatically, so we don't have to worry further about the boundary conditions. In order to find the constants big U, we're going to write the Poisson equation in its weak form, which is always what finite element people do. So equation 1, the Poisson equation, this is the strong form of the equation. We're going to rewrite this. We're going to rewrite it by multiplying the Poisson equation by a test function. So I'm multiplying both sides by v. I'm writing the second derivative of u as u double dashed. And then the weak form means that you don't find a solution that is correct at every point in space. You find a solution that is correct as an integral over space. So in order to find a solution that's correct as an integral, we are going to integrate both sides of this. And then in order to make this tractable, this integral is integrated by parts. So the first part of that is we differentiate that and leave that to get this bit between the limits. And then we differentiate that and integrate that bit. And so you get this term here. And we're also integrating the function on the other side. So from here we can assemble a stiffness matrix to find the unknowns big U. So what we do is we substitute the sum of the basis functions with the unknowns U into equation 5. So equation 5 is the Poisson equation in weak form. And then we had in this equation here, we've got these basis functions V. We're going to use the test functions phi as the, sorry, we're going to use the basis functions phi as the test functions. So the test functions are, the basis functions are 0 on the boundaries. So this term is always going to be 0. So substituting this term into the Poisson equation, we get this equation. So that's the integral of U multiplied by V, a test function, is equal to the integral of the function on the right-hand side multiplied by the test function. That holds for all test functions J. We can take this U, some of the U's outside the integral, because that's fixed. These are fixed in space. And now this term we can evaluate because we know what all these test functions are. So I've evaluated here what this integral is for if I is equal to j, and for if I is a long way away from j. What I would like you to evaluate, given the definition of phi I that you wrote down here, I would like you to evaluate what the integral of phi I, phi j is for if I and j differ by 1. And you'll be able to check your answers in the class. So now we know the function f is known, so we can also evaluate the right-hand side, this right-hand side here, for every value of j. And so equation 7, this equation, becomes a matrix equation. We've got all these different values, a matrix of values for this integral, phi I and phi j. And each of those integrals I'll call a ij. So now we've got this matrix, which is called a stiffness matrix, multiplied by the unknowns is equal to the right-hand side. So we need to solve this matrix equation to find the values u, big U, and hence we've found an approximate solution of the Poisson equation.